Thank you very much for being here. Before I get into this package that we developed, I want to give you a little bit of information about myself. So I am Paul Miles. My background is in mechanical engineering, and I only recently started working in Python. I started a position working for Ralph Smith at NC State in the Department of Mathematics about 2 years ago, and that's really when I first started using Python. So the last couple days have really been eye-opening for me. It's my first time at SciPy, so it's really been impressive to see just what all is out there to use. So I'm honored to be a part of this, and I look forward to your feedback. All right, so what we've been working on is this Python package called pymcmcstat. And what I'm going to go over today, I'm going to give you a brief introduction as to what the package is for, why we specifically decided to develop it. The hardest part probably will be the methodology, where I'm going to try to just give you an overview of the math and the statistics. And admittedly, I don't understand most of the math and the statistics, so many of you are going to be way ahead of me on that. But after we get through that, we're going to go through a basic example, which hopefully gives you a good idea of how the code is used and how you might apply it to your projects. I'm going to highlight, I think, some of the more useful features we've integrated. I'm not going to go into a lot of details with these case studies, but I'll just mention a couple things and sort of maybe good ideas when you're looking to use this. So yeah, let's go ahead and get started. So the purpose of the package is for model calibration or parameter estimation. And we want to do this in the context of uncertainty. So we're acknowledging there's uncertainty that arises for various reasons, so we want to do our calibration in the presence of that uncertainty. And the methodology we use, that will be a Bayesian perspective, which I'll go into momentarily. But really, this particular package we've developed, we designed to mimic a MATLAB toolbox. So my background, I have extensive experience with MATLAB, and my advisor has done a lot of education when it comes to Bayesian methods using this MATLAB toolbox. So we wanted to create a similar Python tool to that. So the API is sort of similar to that. So there's good and bad with that, but that was kind of the motivation. The other aspect of this MCMC, which is what the methodology is we incorporate this delayed rejection algorithm. So don't worry if you don't know what that is. I'm going to just briefly touch on it later on in the talk. All right, so the methodology. I mentioned we're approaching this from a Bayesian perspective, and at the end of the day, all this really means is the goal of the model calibration is within our model we have these parameters, and we're assuming they are random variables. They have some underlying distribution, and we want to figure out what that distribution is. All right, and so from Bayes' equation, we see that we have posterior densities, so those are the probability of our parameter values given whatever data or observations we have to inform that. And Bayes' equation relates this to a likelihood function and a prior function. So the likelihood is describing the likelihood of your observations given your model or your parameters. And then the prior is where you define anything you know a priori about your parameters. So it's sort of a natural framework for these type of problems. Bayes' equation is great, but computationally it's really unrealistic to evaluate it because the denominator requires integrating over r to the p, where p is the number of parameters, so that becomes very expensive real fast, and that's where Markov Chain Monte Carlo methods come in. All right, and I'm not going to go through all the details of MCMC, but I'm really just going to highlight the inner workings. Before I do that, I really want to point out within pymcmcstat, we are making an assumption with regard to the statistical model. So this does narrow the application of the package, but it is still, we believe, useful for a wide variety of potential problems. So we're making this assumption that your observations or your experimental data should be equal to your model response plus some amount of observation error, which is normally distributed with mean zero and some constant variance. All right, so I think this will be a little clearer once we look at an example later on, but as a direct result of assuming this form of your statistical model, you get a very nice looking likelihood function, this Gaussian likelihood function, which depends on your sum of squares error. So the reason this is kind of nice is many people aren't really familiar with Bayesian terminology and likelihoods and priors, but at the end of the day, users of pymcmcstat are primarily responsible for just defining a sum of squares error function. And so they can kind of Even if they're not familiar with the terminology, hopefully they've done some sort of minimization or optimization with sum of squares. Okay, so with that in mind, this is really a crash course on how inside of MCMC we use what's called a Metropolis algorithm to try to infer what these posterior distributions are. And so the way this works is that we start off our procedure with some initial parameter values, which may be from expert knowledge or some initial optimization study. We then go through a set number of MCMC simulations, and each step along the way, what we do is we construct a candidate, and that candidate is really, we're just taking a step away from the previous value, and R in that equation is related to your parameter covariance matrix, so it's essentially mapping to your physical parameter space. So we take this step, we get this proposal, Q star is what I call it, and then we compute the posterior ratio. So this comes directly from Bayes' equation, but as a result of taking this ratio, the denominator in Bayes' equation cancels out, and we're left with a nice expression in which we can compare our likelihood and prior with respect to our candidate, Q star, and with respect to our previous parameter set, Q to the K minus 1. And then at this point, we have this ratio and we make a decision, and the decision is whether or not is this candidate a good candidate or is it a bad candidate. And the idea is if that posterior ratio is greater than 1, we're definitely going to accept it. That's a good thing. I think it's a little easier to simplify this. So taking what I described on the previous slide, if we assume a likelihood function, a Gaussian likelihood function that depends on that sum of squares value, and then assume that your prior distributions are uniform, the priors cancel out, you're left with the likelihood functions, and you can end up putting this posterior ratio in terms of just those sum of square values. So the intuition is if you reduce the error between your model and your data, that's a good thing. And so we're going to accept that parameter value. If it goes up, we're going to accept it based on that ratio. So if it's close to what it was before, it seems reasonable it could still be an okay parameter set, so we'll potentially accept it, but we won't outright reject it. And this allows us to not get stuck in local minima in our error surfaces and things like that. So that's really a crash course on Metropolis, and hopefully that's the worst math. All right, so I think let's look at a basic example, all right? I like simple examples. We're gonna look at some data, and we're gonna make the data so it's really nice data, and it's just gonna follow a linear trend, and we're just gonna say that it has a slope of 2 and an offset of 3, all right? And I'll define this on the next slide, but we're gonna also add some noise to it to make it a little more realistic, and we just specify the amount of variance in that noise. And in our infinite wisdom, we're gonna fit a linear model to our linear trending data. And so here's an example of a potential data set, whatever your quantity of interest is in Y, and then whatever your measurement states are at X, so we can evaluate the model, add some noise to it, however you get your data, all right? How do you actually do the calibration, all right? As I said earlier, the user's primary responsibility is to define this sum of squares function. So the way that pymcmcstat works, it's going to send you a vector Q, so this would be your candidate Q star. It's also going to send you this data structure, and you look at your data, you evaluate your model, and you calculate your sum of squares error however you want to, and you return that value to the code. All right? This is just for this simple example, all that's required to run the MCMC simulation, you create an object, you add the data, you tell it what sum of squares function to use. There's lots of options, which I'll go into more in a little bit, but basically you need to tell it how many MCMC simulations you want to run. You need to tell it what parameters you're interested in. So in this case, the slope M and the offset B, we give it an initial value. It's not exactly the correct value. And then in the case of the offset, I've also applied like a minimum and a maximum. So without knowing it, I've actually implied or enforced some information regarding the prior function, saying that it needs to be within those bounds. But there really isn't too much, hopefully, statistical language here. At that point, you have enough information to run the simulation. It takes a few seconds to get some information about what's going on. But then we need to analyze the results. So if you're not familiar with MCMC, this might be new. For others, this may be boring stuff, which is okay. But the basic idea is we have this Metropolis process, the MCMC. We've been generating these samples, and we want to look at that sampling history to see how it's evolved over time. So you see at the beginning here, we start off with the initial values that we assigned, and then it fairly quickly appears to converge to a distribution centered about reasonable values, close to m equals 2 and b equals 3. So it seems like the algorithm is working the way that we want it to. And then I've added this red line, sort of a general rule of thumb with these MCMC procedures. It takes a little while for you to converge to the correct distribution, so you kind of want to just remove the first part as burn-in. And so our analysis will really focus on just taking that portion of the chain to the right of that red line, and we're calling that, and we'll use that as our representative set of points for the posterior distribution. We can take the burned-in chain and do some sort of kernel density estimate and look at PDFs. We can also look at pairwise correlation, where we literally plot the chains against each other and see if there's any correlation between our parameters. And we can also do things like uncertainty propagation and look at, in this particular example, prediction in credible intervals. Credible intervals are simply a result of propagating those parameter distributions through your model. So essentially you're getting a distribution on your model response. Prediction interval also propagates the uncertainty associated with your observation errors. Kind of a rule of thumb with those 95% prediction intervals is 95% of the time you would expect a future observation to fall within those bounds. Another way to look at it is, of the observations you currently have, you'd probably expect about 95% of those points to be inside those intervals as well. So that's the basic example, and those are some simple diagnostics that are included in the package. Obviously, there's a lot of other plotting routines available if you want to use those. So some of the more advanced features available within the package. So I just highlighted a couple earlier. You need to specify the number of MCMC simulations. There's also different Metropolis algorithms available, and I'm going to go through that more in just a second. You can specify whether or not to update the observation error variance. I'm not going to worry about that too much here. Some bookkeeping tools. A lot of times you're running these simulations, say, on a cluster, because that's where your model's at, and it takes a long time. And so you can be running this and specify, okay, every 1,000 simulations I want you to stop, append the current set of chain results to a file, and then keep going. And that way you can download your file. It could be, you can do binary or text files. You can download it to your local machine, plot it, and see how the simulation is going. But just let it keep running in the background. And so there's other features available as well. So I mentioned the Metropolis algorithm at the beginning. I gave you a crash course. The features that we really want to point out is the addition of what's called adaptation, where as we accept candidates in this algorithm, as we learn more about the proposal distribution, we want to update our estimate for the parameter covariance matrix, which I mentioned this is related to the R in when the process, or in the point where we construct our candidate. By updating that R, we can more efficiently explore our parameter space. So that's a trick that we can use, and there's certain statistical things that have to be satisfied, which I don't know enough to answer, but we can talk about it. And then the other feature that we like is what's called delayed rejection. So instead of outright rejecting a candidate in the standard Metropolis step, when we reach the rejection point, we instead enter this delayed rejection algorithm, where essentially what we do is we go back to the candidate stage and we sample from a narrower proposal distribution. Essentially what I mean is in this R, we basically take a smaller step away from q to the k minus 1, smaller step away from your previous step. So you're going to be more similar to previous step and more likely to have similar values. So you're more likely to accept, and this helps stimulate mixing, so you're not constantly get the same value over and over and over. So we can talk about that more later if you want. All right, so these are the Metropolis algorithms available. So just to highlight, for this problem, we can run, this is just the standard Metropolis Hastings. If you look at the 5,000 burned in value, so that's the last half of the chain, there's actually only about 5% of those that are unique. So it's only accepting just a small percentage of the time. All right, so if we add in the adaptation feature and then run that, we see that it can be bumped up to something like between 21 and 22%. So that's good. By getting more mixing, potentially means you're going to converge the posterior faster, so we like that. What if we just look at delayed rejection? So we're not adapting the covariance matrix, we're just adding delayed rejection. Now we're looking at something closer to 40% acceptance rate, and you see that here there was 2 steps. Stage 1 is your standard Metropolis, and it's about what it was before, and then through this delayed rejection step we see that we're accepting a lot more by sampling from that narrower proposal. Finally, we can add both those features together and get something more along the lines closer to 80%. All right, so that could potentially, you could run fewer MCMC simulations by more efficiently exploring the parameter space. That's why we like this algorithm. All right, so I'm just going to highlight a few really basic features of a couple case studies. So don't worry if you don't know much about these problems. This stems back from when I used to be a mechanical engineer, but it's just a model. It's got parameters in it, and we want to try to figure out what these distributions are. And I just want to highlight some of the problems that you often face when doing this analysis. So as you may have realized, the most expensive part of MCMC is the actual model evaluation. So doing something simple like writing your code in a faster programming language can make a huge difference. That may or may not be an easy thing to do, but just an example for this particular problem, you can see significant computational performance just by putting it in C++. And it's nice to use the C-types package in order to just very cleanly wrap that into your Python scripts. So I have examples of that on the tutorials for the package. Something else that's often common is you may run into a situation where the parameters in your model are not sensitive. So you're doing this calibration and you're never informing what that parameters distribution is. You're getting you're basically just getting a uniform distribution out. So that you may know this from sensitivity analysis, something like that. So you could say that it's not identifiable given the data that you have. So instead, you still want to include it as a model parameter, but you don't want to sample it. So you can just add this keyword argument and set sample equal to false, and then just pass it in as a fixed value. And this is nice because then in the sum of squares function, you can pass in this function and it's the same. It's just unpacking this candidate with all of your model parameters, whatever they may be. But if you later decide to sample this, you can set it to true and not have to change your sum of squares function. So this was another project, and this may be more realistic for what people work on. So this was something fun, getting to work with nuclear engineers. But we're trying to do source localization in a 3D environment, which presents a lot of challenges. One, they don't let you take a radiation source around an urban environment and run experiments. So we had to do this computationally. To do that, we use what's called Monte Carlo end particle simulations. This model gives us a prediction of what you would expect detectors in this domain to give you as readings in terms of counts given a source placed at different points within this domain. So this is a simulated urban environment representing an area of Ann Arbor, Michigan. And it's a complicated domain, different types of buildings, different materials, and so that presents a lot of challenges. But we have to do this numerical approach to represent as best as possible a real-world problem. And so, for example, to simulate 4,000 different source locations and get our expected detector readings for 4,000, so just for 4,000 essentially models, model evaluations, we're looking at 3 to 4 weeks on a supercomputer. So that's not going to work for MCMC, where we may need to do 50,000 or 100,000. So instead, we go back and we use something from scikit-learn. In this case, this was made of the Gaussian process, I think regression model. And I just call it a surrogate model, but basically it's just trained based on a finite set of high-fidelity model simulations. And then we use this really fast surrogate model inside of MCMC to try to infer what our parameters are. In this case, the source location, X, Y, Z, and the source intensity. So I'm not sure how easy it is to see in these plots, but these are essentially two-dimensional probability contours highlighting our posterior distributions for the source location with respect to X and Y, and with respect to X and Z. And so it's probably, there is sort of a darker region, and it's kind of close to the true source, which is denoted by that red star. So this is actually a useful result. Obviously, this is a fairly spread out posterior distribution, but it is realistic given the uncertainty just associated with the physics of the problem. All right, so this is something that we're still working on, but it is what we think it's useful anyway. So coming back to where we started, we developed this package to do model calibration in the presence of uncertainty. The specific implementation was motivated by educational tools that we've been using based on a MATLAB package. So we wanted to provide sort of a similar interface when we're interacting with groups of people. Some are Python users, some are MATLAB users, but we can use the same tools to teach them because it's essentially the same code. It's just in a different language. And so also the addition of that delayed rejection algorithm, which may exist in some other Python packages now, I'm not sure, but that was something that we use a lot, so we wanted to make that available. And then I've highlighted a couple areas where we're using it, and theoretically other people have started using it for their problems as well, and I hope that's going well. So I'd like to thank the people that have been sponsoring this work, the NNSA as well as AFOSR, and certainly my advisor Ralph Smith for letting me take the time to kind of learn how Python works and more or less be successful at it. So I appreciate your attention. Some additional references. Are there any questions?
Thanks, that was really great. I noticed that you had a way to specify the burn-in. Is there any way to do thinning on this?
So in terms of, okay. In terms of thinning just the chain that you have at the end, so I mean it's just a NumPy array, so you can thin it by yourself, or in terms of the plot, I did have another demo where you could specify the max number of points you want to include in the plot. So it's sort of thinning already. So there's 5,000 points, and those plots I actually only plot 500. Yeah.
Hi, thanks for the talk. So my question is related to, it's like a quick question. I'm not familiarized with the MATLAB tool that you mentioned. I'm not an expert in Bayesian statistics, but I do use Bayesian statistical methods for my research, but for that I use R tools like JAX. So I don't know if you're familiarized with that, but if so, I don't know, I think that you should incorporate things that come from the JAX world, because that will allow you to have potentially more users. And I think that it would have been nice to have things like Gilman plots, or things like that in your package. And also, I don't know, are you working towards that? Are you familiarized with JAX?
Yeah, I sort of intentionally didn't include future work on the project because I'm starting a new job in like 3 weeks, and I don't know if they're going to let me work on it. But it's a good point, so maybe we could follow up afterwards. Be good.
Questions?
I was going to ask if you had thoughts or plans, but it sounds like I can only get your thoughts on Hamiltonian methods for this.
Yeah, so like Hamiltonian, Monte Carlo. So obviously there's a lot of tools available for doing MCMC, and like this is nothing compared to say like pymcmcstat. Like I often encourage people to do that, but that's, somebody earlier was calling, that's a high level probabilistic programming approach, and this is sort of this minimalist define a sum of squares function. But I have looked at HMC, certainly very powerful approach as well. Yeah. But there's other tools available for doing that. So I haven't tried to embed it in what I'm doing. Yeah.
Hi, thanks for the talk. I'm also coming from an HMC background, and there was kind of a rule of thumb, not so strict anyways, of targeting your acceptance rate around 45%. Because if it gets too high, your autocorrelation simply gets high and you don't really have that many independent samples. So can you comment on kind of the trade-offs in this algorithm?
Yeah, that's a good point. So I think unfortunately the example I chose that using both delayed rejection and adaptive metropolis was extremely high acceptance rate. And that's more than I would have liked, but I was too lazy to find a better example. So yeah, there's sort of a trade-off when you get too much mixing like that. And I'm not sure what the exact range of acceptable rates are. I try to say anywhere from 20 to 60 is sort of okay. And most of the problems I work at, like the source localization problem, I'm getting around 30 to 48% acceptance with DRAM with both the delayed rejection and the adaptive metropolis put together. So it may just be a product of that simplistic example I was doing. But that's a good question.
Any other questions? So I have a maybe naive question. So is there a good way on this plot? I think you chose 5,000 iterations to stop, say you've converged to the right distribution. Is there a good rule of thumb or a way to automate that?
Oh, so how to choose whether or not you've converged?
Yeah.
Oh, yeah, so actual diagnostics on chains, I didn't go into the diagnostics available. There's a few tools you can look at, like autocorrelation time, some people mentioned that. Those are available. Probably the best one, and this is available, is you can run parallel chains separately and then take those chains and do what's called Gelman-Rubin diagnostics, which is sort of an analysis of the variance of the different chains and how they relate to each other. And that's sort of our robust, they've converged metric. But I haven't automated that, so it's still sort of up to you to take a look and be like, okay, the Gelman-Rubin values are good and the chains look good, and you can also do like energy statistics to say, oh yeah, these are actually the same distributions at the end. So if you've got separate chains and they've converged to the same thing. So I didn't highlight those, but I've touched on them. I can't say that I'm an expert in any of that though. So good question.
Any other questions? If not, let's thank Paul again.